In this video, I would like to take you through Fubini's theorem for functions of two variables which are integrable over a rectangular domain in the plane. We will give a broader set of hypotheses when we actually state the theorem and then prove it, but until we get to the actual theorem statement, you can imagine that the function f we are looking at is continuous as shown in this picture. So later, we will not require f to be continuous, but just for the sake of illustrating the principle, let's just talk about continuous functions for the first few minutes of this video. So in particular, we can imagine S here as the Cartesian product of the intervals from a to b and c to d. So a to b along the x-axis and c to d along the y-axis. So here I've graphed a surface where x and y are coming from the rectangular domain S, and then the z-coordinate is what we get when we evaluate f on that domain S. So this wavy surface is the graph of z equals f of x and y. Now, if you look at the goal that I've stated here at the bottom of this slide, I'm saying that I would like to compute the double integral of f over s by first integrating f with respect to its y-coordinate as a definite integral from c to d. And then we would anti-differentiate the result with respect to x, plug in b, subtract off plugging in a, again in the usual way. Or alternatively, you could flip the order of integration here and anti-differentiate first with respect to x, then with respect to y. Looking at this goal, it might surprise you because for a lot of students, they mistakenly believe that when you evaluate a double integral, that this process of anti-differentiation with respect to one variable at a time is the definition of the double integral, and it's not. So this, what I would call iterated integration, computationally, that is what we often do. So that is what people learn to call double and triple integration, but it is not truly the definition of, say, double or triple Riemann integration. I will take you through that in more detail in just a moment, but before we do that, let me actually just remind you with an example how that one at a time integration works. So imagine here I have the function f of x and y equals y times e to the negative x plus x. And we want to integrate this over the rectangular domain where x is between 0 and 5 and y is between 2 and 4. Now, if I stopped you on the street and said, hey, could you do this double integral for me? This is what I would expect you to do. You could perhaps set this up as integrating first with respect to y and then with respect to x. So here I've written it that way. You would anti-differentiate with respect to y, getting 1/2 y squared times e to the negative x plus xy. Plug in 4, subtract off plugging in 2 for y, leaving you with 6 times e to the negative x plus 2x. Now we just have a single integral. Anti-differentiate that with respect to x, plug in 5, subtract off plugging in 0, and you're left with 31 minus 6e to the negative 5. So I think most people who have gone through multivariable calculus would look at this problem and solve it this way, or perhaps by first anti-differentiating with respect to x and then y, and that's completely normal. But when you do this, you are not using the definition of the double integral in Riemann integration. What you are using is Fubini's theorem. So to illustrate the difference between true Riemann double integration and this process of anti-differentiating one variable at a time, let me go back to the beginning and kind of quickly go through the derivation of Riemann integration from scratch. And as we work through this, I'm going to call this a casual derivation of Fubini's theorem. You could call it a plausibility argument, where I'm going to do like a loose, hand-wavy, fake proof of Fubini's theorem. It looks good, but it's not really rigorous. And then we will do more rigor later. So if you want to see an actual proof, just sit tight. That will come at the end. In the meantime, imagine that we have our rectangular domain S and our continuous function f. When we create the double integral of f over s, what we are doing is computing the volume enclosed between the graph of z equals f of x and y and the domain S in the xy plane. So here I have the solid pink three-dimensional volume. In this picture, it's sitting entirely up in the first octant, so all the volume is positive, but it could dip below the xy plane, and that's okay. Ultimately, the signed volume is what we would like to compute with our double integral. Now, this is a volume computation, but we don't have anything from, say, high school geometry that allows us to directly compute this volume as it's shown to us now. So what we do with Riemann integration is we approximate the volume by breaking it into prisms. So in particular, in this illustration, I've imagined creating a partition of the rectangular base into subrectangles. It's a finite collection of subrectangles. It's always a finite subcollection for any particular partition of the domain. And then over each of those subrectangles, I assign a height to create a three-dimensional prism. So these prisms are these cubes. They look kind of like sticks of butter in this graphic. In this particular illustration, what I did was I picked the minimum value that the continuous function took over each of the bases. So for each of the little subrectangles, I identified the shortest function height to give each of these prisms height in the z direction. Then when I add up the volumes of these prisms, which is not hard to do with geometric methods, it's length times width times height for each one. We add all of those volumes together, and by doing so, what we are creating is called the lower sum of f with respect to this particular partition. The word lower there comes from the fact that I took the function minimal values to create the heights of all of these prisms. Now, this particular partition is just an estimate of the volume. Obviously, it's not the true volume because there's a gap between the prisms that we've created and the true graph of the original function f. So this is just one particular partition. But since f is Riemann integrable, what the definition of Riemann integration tells us to do is imagine all possible ways that we could partition the domain into subrectangles. Then what would be the corresponding lower sums of the function f with respect to each of those possible partitions to create a set of volume estimates. The supremum of that set is what we would call the double integral of f over this domain S. So that's just a review of how Riemann integration is defined. What I really want to emphasize here is that when we partitioned the domain S, this rectangle in the xy plane, we partitioned it into sub-rectangles. So I sliced the domain up in two directions, one direction perpendicular to the x-axis that discretizes the x variable, and the other direction perpendicular to the y-axis to chop up the y domain between C and D. So just keep this idea of sticks of butter in your mind. Fubini's theorem gives us a new perspective on how to estimate the volume enclosed between S and the graph of f. What if I only sliced perpendicular to, say, the x-axis? So here imagine that I'm chopping up the domain on the x-axis between A and B. That creates subintervals along the x-axis. For each subinterval, what we do is we fix one of the x values, graph f over that particular x value, letting y go from C to D. That defines a wavy top to each of these slices. But the idea is that it's the same wave across the subinterval. I hope that makes sense. So it's like for each subinterval along the x-axis, we're creating slices of bread where the top of the slice varies as y changes from C to D, but not side to side along the subinterval. So it's still like a smooth top. So let's see if we can figure out, again, how to do an estimate of the volume enclosed between f and s, by this time estimating that volume with slices of bread. For simplicity, let's just focus on this one particular highlighted slice on the end of our loaf of bread. That's the slice that's closest to you. I've highlighted it here with a lighter shade of blue. Because of the way that we created the top of the bread slice, the front face and the back face are the same. It's the same shape. To compute the volume of this entire slice, we need to multiply the area of the blue face times the thickness of the slice, like the thickness of the bread. It's a base times height volume computation where the base is this vertical blue face and the height is actually lying on its side. It's this little thickness. Let me go ahead and mention that the thickness of the bread, it makes sense to call that delta xi. That's just the spacing between the slices. All right, so for convenience, let's call that slice closest to us the ith slice. And over on the right, I've tried to graph the face of the bread. That's the area that we need to compute. So that's like saying, fix some x coordinate in this ith slice, and then let y vary from C to D. So this is really a graph of a function of one variable. So if I handed you this picture and I said, what is the area under the graph of f? How could we compute that? Hopefully you would say, that's just a definite integral computation, area under the curve. We would anti-differentiate this function with respect to y, plug in d and plug in c using the fundamental theorem of calculus. For notational convenience, I'm going to give that measurement the name of a new function g. It's a function of the fixed x that we chose to be the representative for the subinterval. So I will say g of xi star, where that's like our slice point along the x-axis, is equal to the definite integral from c to d of f of that fixed slice value comma y. Were you to actually anti-differentiate this, you would plug in for y and be left with a function of xi star. Okay, so let's now add up the total slice volumes to approximate the volume enclosed under the graph of f. Imagine that we have n slices, and for each of those slices, we would do the area of the face, that's a definite integral computation that we have here, times the thickness of the bread, delta xi. And then we would add up those individual slice volumes from 1 to n. That definite integral in the middle is exactly what we're calling gi star, so let me just make that replacement. And I want you now to take a moment to look at this expression and see if it speaks to you. So does this notation here remind you of any kind of computation that you did perhaps back in single variable calculus? What it should remind you of back in single variable calculus is a Riemann sum expression. It looks like a Riemann sum for the function g. So if we imagine slicing more and more, letting our bread slices get thinner and thinner and the number of our slices grow larger and larger, we would be more and more finely approximating the volume enclosed under the graph of f, but then computationally, we would expect our Riemann sum expression here to turn into the definite integral from a to b of the function g of x integrated with respect to x. But then what is g of x? It's an integral of f of x and y just with respect to y. So here we arrive at our double integral expression, but again, this is just a casual derivation. There was quite a bit of hand waving happening here, but I think it's useful to see this slicing mechanism that goes into the story behind Fubini's theorem. We will prove this formula rigorously in just a few minutes. All right, so let's go back to our function. I just created bread slices by chopping perpendicular to the x-axis. What if I went perpendicular to the y-axis instead? It should work just as well. So doing this much faster, imagine that I sliced only perpendicular to the y-axis to partition the domain from C to D. Now we have another loaf of bread sliced differently. Let's say we slice it into m slices. The thickness of each of those slices is some delta y measurement. We can call it delta y sub j. And then if we add up the volume of these individual slices of bread, we're approximating the loaf's true volume. Again, slicing more and more finely leads us to another double integral where, again, what we've done is really just set this up as two single-dimensional integrals with one nested inside of the other. Here, notice the difference is that we're switching the order of integration. So going through the same steps but slicing differently leads us to first anti-differentiate f with respect to x and then with respect to y. So this change in perspective, going from the true definition of Riemann integration on the left, subdividing the original domain into sub-rectangles and creating these rectangular prisms, going from that perspective to this slicing perspective, and wanting to conclude that, at least in the context of having a continuous function over a nice domain, that these ways of slicing are equivalent is really what Fubini's theorem is giving us. The one on the left is an illustration of the true double integral of f as a Riemann double integral. On the right, on the other hand, what we have is a pair of iterated single-dimensional integrals. As I alluded to at the start of this lecture, while the pictures I've been showing you were of a continuous function f, that is much stronger than you actually need for Fubini's theorem. So here is perhaps the broadest viewpoint that we could take. Suppose that we have a rectangular domain in the plane as before, but this time let f be just Riemann integrable. So it may be continuous, but it certainly does not need to be. If for every choice of x that you could make between a and b, the integral of f of x and y dy from y equals c to y equals d exists, so in other words, you plug x into f and then you're left with a function of y, if that function is integrable, then the double integral of f over s could be computed by first integrating f with respect to y and then with respect to x. This is the equality that we will prove. So this hypothesis that in any x equals constant slice, we can integrate f with respect to y allows us to evaluate the double integral of f over s by first integrating with respect to y and then with respect to x. Here the order matters. On the other hand, if we know that f is also integrable in any y equals constant slice, so here if we fix y and then integrate f with respect to x from x equals a to x equals b, if that also exists, then we could reverse the order. So we could integrate f first with respect to x and then with respect to y. And of course, you can figure out that if only that second one existed, then we would only have the option on the right. Now, we only need to prove the first equality on this slide. We won't need to do another proof of the second hypothesis because the proof that we're about to do, showing the first equality on this slide, would also work for the second equality, just interchanging the roles of x and y. Okay, so this is all we are going to need to prove, just the equality of these two expressions. What we are going to do in this proof is work with the partition, assuming only that f is Riemann integrable and that for any choice of x we make between a and b, the integral from c to d of f of x and y dy exists. Now what this hypothesis does is say, pick any x you like from the x domain. We can get back a number, which is the integral from c to d of f of x and y integrated with respect to y. That's the action of a function. So let's bring in this function g. It's actually essentially the same as the g that we met in the derivation. And we'll say for each choice of x you make, g of x is the corresponding number you get by doing this integral. Our goal is to show that g itself is a Riemann integrable function from x equals a to x equals b using partitions. Now, typically when we talk about Riemann integrable functions, the first thing we want to know is that the function is bounded, so that will be the first observation we make. Since f is bounded by hypothesis, by say some number capital B, if we compute the size of g of x, then that's the absolute value of the definite integral from c to d of f of x and y dy, but using one of our properties of integration, we can go up in size by integrating from c to d the absolute value of f of x and y. The integrand is now less than or equal to this capital B. So with the monotonicity property of the Riemann integral, we can say that this expression is less than or equal to capital B times d minus c. Thus, g is also bounded. Now that we know that g is at least bounded, let's move on to making our partition. So given that f is Riemann integrable on the rectangular domain S, go ahead and chop it up into some finite collection of subrectangles. We will call the partition of S P, where here I'm writing that as a Cartesian product of slice points along the x-axis between A and B, and slice points along the y-axis between C and D. Notice that that first collection of points between A and B defines a partition for G, because G is a function of x. So to distinguish between the two partitions, let's call that P sub x, the partition along the x-axis. Okay, by doing this partition, we're creating a family of subrectangles, S sub ij, where I will index us along the x-axis and j will index us along the y-axis. So imagine that we've broken the interval from A to B up into little n subintervals. So the index I here goes from 1 to n. And we've broken the interval along the y-axis from C to D up into little m subintervals. So here the index j goes from 1 to m. And then to remind you of notation that we've seen before, let delta x sub I denote the width of the ith subinterval between A and B along the x-axis, and let delta y sub j denote the width of the jth subinterval between C and D along the y-axis. So here I've reminded you of how to compute those two widths. Now take any pair of indices I and j. Since f and g are bounded functions, we can define the following family of infima and suprema values. So in the traditional way, we will let little m sub ij denote the infimum of the set of outputs that f takes over the ijth subrectangle. Likewise, capital M sub ij will be the supremum of the set of outputs for f over the ijth subrectangle. On the other hand, g is just a function of x. So to try to distinguish between infima for f and infima for g, and suprema for f and suprema for g, I'm putting the superscript g up here. Let little m sub I superscript g denote the infimum of the set of outputs for g in the ith subinterval between A and B, and likewise let capital M sub I with the superscript of g denote the supremum of the set of outputs that g has over the ith subinterval. So we evaluate f on the subrectangles, but g only along subintervals because it's just a function of the x variable. Next, just fix any value of I between 1 and n. For every x in the ith subinterval, we're going to write g of x in a clever way. So first, by definition, g of x is the integral from c to d of f of that fixed x value comma y dy. But now let's break that integral up into m little subintegrals. So I've used the partition of the y-coordinate to rewrite the integral from c to d as a sum of the integrals taking us basically across all the slice points from the partition. If you look at that first integral from c to y sub 1, here I is fixed, but j equals 1 for that particular expression. If you look at the second integral I wrote down, again, I is fixed, but now j is 2. In the final integral expression, I is still fixed, but j is m. So now looking back at that first integral, f of x and y, whatever x is, this is an output in the subrectangle for I, 1. So we would go up in size by replacing that integrand with the supremum of all of the outputs of f from the I, 1 subrectangle, and that's exactly what we called that supremum value, capital M sub I1. Similarly, the second integrand, we go up in size to the supremum of the set of outputs for f over the I2 subrectangle, but that's capital M sub I2, all the way through capital M sub I M, where I apologize for the overuse of the letter M there. That's referring to the number of slices along the y-axis. So that's J equals M. Now, each of these integrands is constant. So if you were to evaluate each of these integrands, it would just be that constant integrand value for each one times the width of the subinterval. So we could write this as a sum going from j equals 1 through the number of slices m sub ij, where here I is fixed, and then delta y sub j. That's the width of each of the domains of integration that we have on the line above. I would like for you to pause here, take a moment just to work through this, make sure you agree with this decomposition in the final summation form that I've given you, and then see what your conclusion would look like if from the second to the third line, instead of going up to f's suprema, we went down to f's infima. All right, what I hope you concluded is that if you go down, we can say that g of x is greater than or equal to a similar sum, but this time replacing the suprema values with the infima. All right, let's put this all together. For each index I taking us from A to B, and then for any choice of x in the ith subinterval, this triple inequality is what we've just concluded. Notice here that whatever x is, it's in the ith subinterval, so g of x is an output from the ith subinterval. We've already named the infimum and supremum of the set of outputs from the ith subinterval. We called them little m sub I superscript g and capital M sub I superscript g. So those two terms I've now put in the middle are the infimum and supremum of g over the ith subinterval. Let me justify that I'm still preserving the inequality. Notice that on the first line of the slide, we are saying that that summation on the left is a lower bound for the set of outputs for g, because it's less than or equal to g of x, whatever x was in the ith subinterval. Since it's a lower bound, it's less than or equal to the greatest lower bound, in other words, the infimum. On the other hand, for the summation on the right, we are now saying that that is an upper bound for the set of outputs of g over the ith subinterval. So since it's an upper bound, it's greater than or equal to the least upper bound, in other words, the supremum. And then infima are always less than or equal to suprema. So we have this chain of 4 expressions appropriately related to each other this way. Okay, now what we're going to do with these 4 expressions is multiply each of them by delta x sub I. That's a positive quantity. It's just the width of the ith subinterval, so we preserve the inequality. This chain of inequalities is true for every index I from I equals 1 to I equals n. What that allows us to do is take that expression on the left, and if we added all of the expressions on the left together for each choice of I, it would be less than or equal to that second term added to itself for every choice of I, which would be less than or equal to the third term added to itself for every choice of I, which would be less than or equal to the summation on the right added to itself for every choice of I. In other words, what I'm trying to say is add up these expressions from I equals 1 to I equals n, taking us across all of the subintervals we form along the x-axis, and we arrive at this inequality. I would like for you to take a moment to read through these 4 expressions and try to come up with the best name for each. I claim that each of them gives us a recognizable expression for f and g. So each one of these is computing something that we have given a name to in the past. For the expression on the left, that double summation, letting I go from 1 to n and j go from 1 to m, is going to take us across every subrectangle created by the partition P of the rectangular domain S. And then for each subrectangle, we are multiplying the infimum of f with the area of the base, because notice we have a product of side lengths. So we have infimum heights times area of the base. Similar over on the right, we have suprema heights for f times area of the base. So both of those you should recognize. And then in the middle, we are going across the subintervals along the x-axis. That's the domain for g. And for each subinterval, we are multiplying either the infimum or the supremum of g times the width of the subinterval. So that's creating a very similar notion for g. And I hope what you arrived at is that the expression on the left is the lower sum of f with respect to the partition P. The expression on the right is the upper sum of f with respect to the partition P. And then in the middle, we have the lower and upper sums of g with respect to the partition P sub x, just taking us along the x-axis. Okay, I need more room, so let's slide that to the top. If you look at the relation on the left, it does give you the feeling that the lower integral of g is greater than or equal to the lower integral of f. but those two numbers are computed by taking suprema of lower sums with respect to different partitions, because these two functions have different domains. So I just want to be very careful here. I'm going to do a quick proof by contradiction. For the sake of contradiction, suppose that the lower integral of f, which is defined as the supremum of all lower sums of f with respect to every possible partition of f's rectangular domain, suppose that is greater than the lower integral of g, which is defined as the supremum of all possible lower sums with respect to all possible partitions of g's domain. If that were the case, then by the criterion for sups and nths, we could identify some specific partition, which I'm going to call p prime, so that the lower sum of f with respect to p prime, that's one particular lower sum, is greater than the lower integral of g. But from p prime, I can extract a partition of g's domain by doing what we call p prime sub x, just looking at how we chopped up the x-axis when we created the partition p prime. That would have to be less than or equal to the lower integral of g, because it's a member of the set that the lower integral is the supremum of. However, this contradicts the line at the top, because the relationship on the first line of this slide is true for any starting partition of S, including p prime. So indeed, this particular relationship does allow us to conclude that the lower integral of f over S is less than or equal to the lower integral of g from a to b. And before I proceed, let me just remind you that for a bounded function on some domain, the lower integral over that domain always exists. That just relies on boundedness of the function. So I can write down lower integral of g before I know that g is integrable. As long as it's bounded, this quantity exists. You can pause here if you'd like and write down a very similar proof by contradiction that the upper integral of g from a to b is less than or equal to the upper integral of f over s. It's the exact same reasoning that we already have on this slide. So let me just go ahead and use it. The lower integral of g is less than or equal to the upper integral of g. That's just a fact about lower and upper integrals for all bounded functions on their domain. And now, again, that's less than or equal to the upper integral of f. But on the very left and very right side of this new chain of inequalities, I actually have equality because f is known to be integrable. So the integral of f over s exists, and it equals its lower and upper integral. Therefore, all of these interior less than or equal to symbols are actually just pure equalities. So we can say that g itself is integrable. In other words, the definite integral from c to d of f of x and y integrated with respect to y, that is an integrable quantity from a to b. This iterated one-at-a-time computation can be done. And we know it's equal to the quantity on the left and right-hand side. It's being squeezed to the double integral of f over s. So to summarize, what we have shown is that if you can integrate f in any x equals constant slice, so if the definite integral from c to d of f of x and y integrated with respect to y, if that exists, then you could then take that and integrate it with respect to x from x equals a to x equals b. That is our familiar method of iterated integration like we had in that explicit example at the start of this video, and we know now that it is equivalent to the double integral of f over s. Okay, let's go back to the statement of Fubini's theorem. So we have shown the equality of the two expressions on the left. As I've already mentioned, but maybe now it will resonate with you more, if in any y equals constant slice you can integrate f of x and y from x equals a to x equals b, then you could also compute the double integral of f over s by first integrating with respect to x and then y, as I've done over on the right side of this slide. And then since both of those iterations are equal to the same number, they're equal to each other. So if f is Riemann integrable in every x equals constant and y equals constant slice, then not only can you compute the double integral of f by doing iterated integration, but you could also reverse the order. At this point, we have finished our rigorous proof. Let me just mention that context that we were looking at the beginning of this video. If it were the case that your function f was actually continuous, you can prove that the integral of f will exist in any of these slices. So your hypotheses for Fubini's theorem will automatically be satisfied. You can do iterated integration, and you can also reverse the order. That's not too hard to show. Let's wrap up this discussion by just mentioning that often in multivariable calculus, we integrate over domains which look irregular. So for example, integrating over a solid disk like we have on the left, that's pretty common. You could have a triangular domain like over on the right. If you start with a domain like this, remember how we built up our machinery for Riemann integration? We took domains like this and we enclosed them in rectangles whose sides were parallel to the coordinate axes. We extended our function to the larger domain by setting it to be 0 outside of the original domain but inside of the rectangle. So that's how you can apply Fubini's theorem to domains that don't look as regular, is you imagine first enclosing those domains in nice rectangles. Suppose that your function f was a function of the disk on the left. If the set of points where f was not continuous was a set of measure 0, then when we extend the function to this rectangle and say look in any x equals constant slice, where might we have picked up more discontinuities? Well, we preserve the behavior of f inside the disk, and then outside the disk, f is a constant 0. So the only danger here is that we might have picked up points of discontinuity on the boundary, but that's just 2 more points. Similarly, if I look over at the triangle on the right and imagine slicing into this domain with any y equals constant slice, the behavior of f inside the triangle is preserved, and outside of the triangle it's a constant 0. So it's possible that by extending this triangle to a rectangle, kind of growing the domain, it's possible that we've added 2 more points of discontinuity, but that won't change the Riemann integrability of this function. Okay, so I just wanted to mention that because often in multivariable calculus, not only do we do iterated integration, but we also integrate over domains which are not rectangles. However, Fubini's theorem adapts to those contexts very nicely. That's everything I wanted to say about Fubini's theorem in this video. Thank you for your attention.